What's going on, people? So I'm going to make a short video how to solve this problem. I figure repeatedly add all its digits until the result has only one digit. So I was thinking of converting to string and then do while length of num s is greater than 1. Keep doing this, and then at the end you want to return the sum. Okay, so at the end you're going to do okay. So return the integer. Okay, so we take num sum, and then I have to iterate. So the reason why I'm doing a string is so I can iterate through it. So I'll do in num s. Start out with some local sum 0, and take the local sum and plus or equal to int n, and then at the end update num s to be equal to string local sum. So the time complexity for this is yeah, so it's kind of interesting. So I mean, the time complexity for this is just going to be the regular thing. Okay, is this interesting? I don't know if it's interesting, but yeah, these are the results that you're getting. And then yeah, this is the problem. Repeatedly add this until the result has only one digit. So that's what you did here. So you did it until it only has one digit. And I mean, because I'm using a while loop, this is taking up some time. Like, so how can I improve this code? This is something I'm always trying to work on. Also, another thing is, yeah, so basically what this is doing though, the idea, the concept is just, I'm creating a string from num. Yes, I'm creating a string so I can iterate through that string. As long as the length of the string is greater than 1, I'm going to keep iterating through. And sorry, I paused there because I had to yawn. But yeah, so I keep summing these up, taking in and adding them onto this value, and then converting it to a string, and just keep doing that and convert it back to an int. And it says you can do this in O of 1 runtime, so it's probably bit manipulation. I'll see if this passes. How can I do the bit manipulation? The first issue is, how do you check if the value is a 1? Well, the only way to be able to do that is to maybe bit mask it. So I could bit mask it, but at the same time, even if I bit mask, I don't know if that will work. So I mean, I'll think about it. I'll look at the hints because I actually don't know how to do it. I don't get it. It says the digital root, also repeated digital sum of a natural number in a given number base, is the single digit value obtained by an iterative process of summing digits. The process continues until a single digit number is reached. Yeah, so I don't understand. In mathematics, the digit sum and natural number is sum of all digits. Okay, so sum of all digits. That's what a digit sum is. Yes, a digit sum of this would be 9 plus 0. Okay. So you're watching me learn this for the first time. I'm gonna try to learn how to do this in O1 time complexity. I don't feel this is. It's called digital root. You use the result from the previous iteration to compute the digit sum. Isn't this what I did? The digital root of number is equal to the remainder when that number is divided by 9. This is weird. So they're saying here that the digital root of a number okay. So these are the two people who contributed. The digital root of a number is equal to the remainder when that number is divided by 9. Divided by 9. The digital root of a number is equal to the remainder when that number is divided by 9. The digital root of a number is equal to the remainder when that number is divided by 9. So 1 plus 2 plus 3 plus 4 plus 5 equals 15. So what's 15 divided by 9? What's the remainder? The remainder is 6, right? So the digital root is 6. If the remainder is 0, so let's say it's actually divisible by 9, and the number is greater than 0, then the digital root is 9. If the number is 0, then the digital root of the number is 0. A shortcut to finding digital root, casting on that. Consider number 2, 7, its digital root is 5 because 2 plus 7 plus 5 plus 1 plus 8, which is 23. 23 divided by 9 gives you a remainder of 5. Now the digital sum can also be calculated by simply grouping, where the ungrouped value 5 is the digital root, since 2 plus 7 equals 9 and 1 plus 8 equals 9 are eliminated from the calculation. But will that always work, or does that only work in this special case where these were equal to 9? If we multiply, okay, let's look at some properties of digital root. Maybe that will help out. If we multiply any number by 9, the digital root will always be 9. Okay, if we multiply any number by 9, the digital root will always be 9. If we divide any number by 9, the digital root of that number will be the remainder. Multiplication magic with 9, we know that. Okay, what is this? Application of digital root. When the numbers are added, subtracted, multiplied, divided, their digital sums will also be added, subtracted, multiplied, divided, subtracted. So the digital sums can be used to check the accuracy of the answer. I never knew that. Validating addition. So you add these up, you get 81. Clearly the digital root of 45723 is 3. Clearly, right? Clearly. Just add 4 plus 5, 9. 2 plus 3, 5. Is the digital root always going to be one of the digits? Okay, 5 is one of the digits. 6 is not one of the digits. Okay, so it's not always one of the digits. So here, the digital root of this is 2, and the digital root of this is 5. Now, using the digital root as 3 plus 2. So the digital root should be the sum of the previous two digital roots. That's interesting. And here multiplication. But you have to know the fact that the digital root of 30 is 3. I never knew that. In all my math classes, I don't think I ever heard of this thing called digital roots. Okay. Make sure I understand it. Look at some other resources. Until the new has only one digit. It's called the additive persistent. I mean, okay, so if I use a digital root, so okay, let's just put this over here. Let's say using the digital root, I'll just say that. It's kind of interesting. I don't know why I'm wondering, but I'm wondering like why. Alright, well, that's interesting. Oops, what am I clicking on? Okay, so if I'm going to do the digital root, basically what I have to do is it was if rem doesn't equal 0, else return 9. Also one other case, if num equals 0, it returns 0. So I just get rid of the whole 0 case. So it should return 9 to be the digital sum if rem is equal to 0. If it's not equal to 0, then we're just going to return rem. I think that's the digital root explained. Whoops. That's bad syntax. Well, okay, I guess that's fun. Just have to learn a math trick for it. Okay. Alright, cool. Yeah, so thank you for watching this video. I just learned about digital roots, and yeah, to solve that problem, and that's it. I'm all up to date, it looks like, for this. Looks like I'm all up to date. Oh, I missed 2 during that week, and I missed 1 during that week. Kind of unfortunate. Keeps happening to me. But yeah, thank you for watching.